Welcome, and thank you very much for joining this presentation titled Improving Chip Design Performance and Productivity Using Machine Learning. My name is Narender Hanchate. I'm a senior machine learning architect at Cadence Design Systems, responsible for developing EDA tools with latest machine learning technologies, and I'll be presenting this session today. Let's first start by setting up some context to this presentation. Semiconductor industry is experiencing a resonance. What I mean by that is new application and technologies are driving demand for more compute power and functionality in devices that we use today. We are experiencing a strong growth based on new technologies like 5G, autonomous driving, hyperscale compute, Internet of Things, and many more. We all want more powerful devices, higher performance, better graphics, longer battery life. This is triggering an explosion in chip sizes and the complexity. Take GPU for example. A few years ago, 1080p was considered a high resolution, but today 4K displays are becoming a standard. Some high-end devices even support 8K resolution. So a graphics design is significantly large and more complex today. And to add on that, chip designers are moving to newer and advanced process nodes. The standard cell libraries are becoming bigger and bigger, and there are many more PVT corners that need to be considered before a chip is signed off. All these things are making chip design a lot more complicated, and it's really difficult for implementation and engineering teams to keep up. Hence, the need of the hour is not just the advanced EDA tools, but also need automation of CAD flows and methodologies to enable the design teams to take on these large and complex implementation projects. So what is the role of machine learning here, and why is it useful for EDA type applications? EDA is full of NP-hard and NP-complete problems, which are not trivial to solve and can easily result in infeasible runtimes due to its exponential nature. To avoid longer runtimes, EDA tools use various techniques with different trade-offs to solve these complex NP-hard problems. For example, on the left side you have heuristic systems which are based on the experience and can be used to guide the outcome of an algorithm, and more often than not result in over-design. On the other hand, you have predictive systems that are used to estimate the outcomes without having to actually compute the exact answer. For example, timing margins provide a blanket mechanism to account for any gaps in characterization. So designers have been accustomed to influencing the designs either with heuristic systems or predictive systems in one way or another. However, this is very imprecise approach and not ideal. It can lead to over-design or additional unnecessary margins. It turns out that machine learning is a much better technique to manage by learning about the actual design and then applying the learning to the implementation flow. This avoids the designer to figure out what kind of constraints that needs to be manually generated. And more often than not, that's where the struggle is today. This is where Cerebrus technology comes into picture. Let's first look at the traditional flow. When engineering team starts a new design, they often go through a period of optimizing the CAD flow and develop a methodology which is specific to the design which they are implementing. The implementation flow is also dependent on the required goals for the design. For example, a low power flow for an IoT kind of a device will be very different compared to high performance CPU flow. Today this process is very manual. The block engineer will start with an existing flow, probably inherited from a previous project, and runs the new design to generate some initial results. Based on these initial results, the designer will change some of the flow parameters. These flow parameters could be as simple as tool options or design constraints or a change in the floor plan. The design is then rerun using these updated flow parameters and new results are generated. The engineer then has to manually review these results and decide if the flow change had helped him meet the design goals, or if not, then he has to decide on what needs to be changed next. This process continues until either the design goals are met or the engineer runs out of the time and has to tape out with non-optimal results. Each iteration of the design generates an enormous quantity of data, which is impossible for an engineer to absorb and make accurate decisions. On top of this is an error-prone process as well. That's because the human brain is not well suited to process all this historical information. For example, after manual iteration number 10, you probably would have forgotten what has happened in iteration number 1. However, this whole manual flow optimization process is an ideal application for both data analytics and machine learning decision making. Cerebrus is based on a reinforcement machine learning approach that automates the flow optimization, which makes an engineering team more productive. The inputs are exactly same as the manual approach. We take an initial flow and an RTL design. The engineer then defines Cerebrus flow optimization goals, such as whether low power is important to him, or high performance, or a balance of both. Based on these goals, Cerebrus will create and run flow scenarios which will decide what tool options or design constraints or library configurations need to be modified so as to meet the designer's goals. The reinforcement machine learning based approach quickly converges on an optimized flow that meets the goals with very little engineer effort required to enable the designers to work on multiple projects. We have also found that machine learning can analyze large quantities of data, and this is by analyzing these data, it can find some solutions which a human engineer would naturally not try, resulting in a better PPA. Cerebrus is based on 3 key technologies. Cadence has invested in a multi-year R&D effort, creating a unique reinforcement machine learning engine, which enables Cerebrus automated flow optimization to deliver better engineering team productivity as well as PPA improvements. Cerebrus is a full flow RTL to GDS2 optimization tool. This is critically important as the flow changes during Janus RTL synthesis will affect later flow changes during Innovus implementation and vice versa. So you have to consider the full flow to achieve a global PPA improvements. If only one stage of the flow is considered, then you will never find the optimal PPA solution. To run the different flow scenarios, Cerebrus utilizes scalable and distributed computing, which can be run on-premise or in cloud. It is a combination of these 3 technologies, reinforcement learning, full flow optimization, and distributed computing, that enables Cerebrus. Now let's get into the details of how Cerebrus works. As the designs and CAD flow are becoming more complex, it is computationally infeasible to evaluate every hyperparameter combination to achieve the best possible PPA. Cerebrus efficiently optimizes the design flow using a powerful reinforcement machine learning engine. It works on the principle of generating the state space on the fly by combining hyperparameters to generate a flow scenario. It then generates the actions for expected improvements through a continuous rewarding mechanism. The RL engine efficiently optimizes both the breadth of the flow scenarios and the depth of the flow phases throughout the full flow. If the full flow scenario is not generating an improved results, then RL engine will terminate the run immediately and use the workstation for a different flow scenario. In this way, Cerebrus makes efficient use of available compute resources. The reinforcement machine learning model is automatically saved to transfer full flow learnings from one design to another, helping Cerebrus converge even faster, providing a significant boost to productivity and PPA. The digital design has multiple levels of abstraction and typically starts with a high-level description of what it's supposed to do, written in either System C or System Verilog. This is then compiled using high-level synthesis tool like Stratus, where all the architectural decisions and optimizations are made. At this stage, designer has to plan for testability by inserting DFT through modus. The RTL thus generated by Stratus is converted into gate-level implementation using Janus. Innovus takes this gate-level netlist through the back-end physical implementation flow to generate GDS2. This GDS2 database then goes through a rigorous electrical and physical sign-off checks before tape-out. This is how the full design flow works. The point I'm trying to make here is that there are several optimizations that happen throughout the design abstraction, and decisions have to be made to achieve best possible PPA. Cerebrus works with all the industry-leading tools provided by Cadence, and then they form the basis of Cerebrus optimization. Now let's look at how Cerebrus uses reinforcement machine learning and distributed computing. Cerebrus includes Cadence reinforcement learning engine and a fault-tolerant system to efficiently manage the distributed workload across multiple computing nodes. The initial inputs are design specifications based on netlist or RTL, and a baseline flow which runs these design specifications through the implementation flow. One of the important aspects of Cerebrus which I want to highlight here is that it does not require any modifications whatsoever to the baseline flow, so the startup time to run Cerebrus is practically zero. The designer then specifies flow optimization goals such as what is important to him, like high performance or low power or a combination of both. So Cerebrus understands what kind of optimized flow is required to be generated. Clearly, a high performance CPU flow will look very different to a low power flow. So it is very important for the designers to influence the flow optimization process. Based on these optimization goals, Cerebrus will create different flow scenarios and start running them on distributed farm, which can be on-prem or on the cloud. Flow scenarios range from simple tool options to complex high-level design optimization, such as floor plan optimization, which uses Innovus's mixed place technology to concurrently resize the floor plan size and shape along with placing the macros. These flow scenarios will generate design metrics which are then fed back into reinforcement machine learning engine in real time. The machine learning engine is continuously updated with data as the flow is running and has ability to predict if a run is going to converge on its goals or not. If the run is not showing any promise, it will immediately be terminated and the new run will be started to reuse the available CPU resource. This is much more efficient than allowing each flow scenario to run all the way through the flow before doing any data analysis. The RL engine is key to ensuring the full flow optimization converges quickly. It is not computationally efficient to just run every possible combination with flow options to pick the best result. RL allows Cerebrus to learn which flow options are effective on a particular design, so the flow optimization can converge much more quickly. On completion, Cerebrus generates a recipe that captures the optimized flow, which can then be replayed as a one-shot flow on future revisions of the same design. Also, a machine learning model is generated and saved that can be used to transfer learning from one design to another design. Reusing this model as a starting point for future Cerebrus flow optimization will significantly reduce the learning time for future projects. Now that we have gone through how Cerebrus works, let's look at some of the results. This is a typical 5 nanometer high performance mobile 3.5 GHz CPU design. The designer used Cerebrus to automatically optimize the implementation flow to improve both power and performance. You can clearly see that the results are quite significant with a 420 MHz improvement in performance and also showing the good power reduction at the same time. This was achieved by one engineer using Cerebrus for about 2 weeks. If the designer tried this flow manually, then it would have taken many engineers for many more months. Even then, it is questionable that if these PPA numbers would have been achieved through manual exploration. This is a great example of productivity benefits that Cerebrus enables. The previous example was based on tool option changes to optimize the implementation flow, which achieved better PPA improvements. However, Cerebrus is also able to optimize the design itself, which is much higher level of optimization. Here is an interesting example showing how Cerebrus can do high-level floor plan optimization. This is a 12 nanometer 2 GHz CPU design, and the designer wanted to use Cerebrus to optimize the floor plan and implementation flow for better power and performance simultaneously. Using the Cerebrus floor plan optimization capability, Cerebrus was able to dynamically change the size and aspect ratio of floor plan and use the Innovus's mixed placer technology to relocate the macros in the resized floor plan completely automatically. This Cerebrus optimized flow and floor plan resulted in over 200 MHz CPU performance improvements with good reduction in leakage power. Cerebrus was able to come up with an optimized floor plan much more quickly than manual iterative approaches could have achieved. A number of customers are already benefiting from Cerebrus full flow optimization technology. For example, Renesas uses Cerebrus as they develop new products on various different process nodes and have already seen success with their floor plan optimization capability. Also, as part of their design technology optimization programs, Samsung Foundry are using Cerebrus to quickly develop flows for new process nodes and design projects, delivering better power results much more quickly than previously used manual flow development process. So to conclude with, Cerebrus is the next revolution in the chip design. Using a unique reinforcement machine learning engine developed by Cadence, Cerebrus delivers better design power, performance, and area results more quickly. Cerebrus provides a completely automated, machine learning driven, full flow optimization technology which utilizes the industry-leading Cadence digital implementation and sign-off flows, enabling better engineering team productivity so that more system-on-chip designers can implement designs concurrently. And also, Cerebrus uses the latest scalable and distributed computing technology, either on-prem or cloud computing resources to enable efficient and scalable chip designs for ever-increasing size and complexity of today's products. If you would like to understand more about how Cerebrus reinforcement learning flow optimization works, take a look at the product page at cadence.com/go/Cerebrus. This page contains a lot more information such as white papers and videos, and also you can always contact local Cerebrus support team. Many thanks for your time and attention today.